Good afternoon, everyone. Welcome to another riveting episode of Dave Does Math from Home. Today we're talking about section 2.4. This is our section on infinite limits, and I'm going to have to open it up with a little bit of bad news. Friends, I have lied to you, which, for those of you that have actually had me in class, should be no surprise. Lying is one of my favorite things to do. In this case, I've lied to you very recently about how to talk about limits when there are vertical asymptotes involved. When we were doing section 2.3, analytical limits, we did a couple examples that involved rational functions. Those rational functions had vertical asymptotes. A lot of those rational functions had little holes in them as well. And we found out that when we tried to take the limit at those sort of problem points, if you try to take the limit of a rational function at a point that's not a problem, then there's no problem. You can just evaluate the function, you get the limit, it's fine. When we were trying to use the limits to figure out what happened to these rational functions at some of the problem points, like points that would make the denominator 0, that's when plan A didn't work and we had to switch to plan B or plan C. Plan B works when you have what's called a removable discontinuity. So it's a fancy word for the hole in the graph. You can figure out where that hole is using plan B. But we also ended up in a couple situations where we had plan B didn't work and we had to go to plan C. Plan C was the limit did not exist, and that's what we did when we had a vertical asymptote. And I said the limit does not exist, and that was it. But there's more. I lied. We can talk a little bit more about those limits. So for starters, let's kind of throw up a graph of a rational function so that we can talk about what these limits look like graphically, and then we'll talk about what to do with them analytically. So let's say we've got something 4, 5, 6, 1, 2, 3. Let's say we've got a vertical asymptote here at x equals 3, and maybe we've got another one back here at x equals -2. So maybe our function's doing something like this. This is a pretty reasonable expectation for a graph of a rational function. I'm going to change it a little bit. Let's do this. Make that a little closer. There we go. This is a reasonable graph for a rational function. We could imagine a graph looking like this with our vertical asymptotes and our x-intercept, and we probably got a horizontal asymptote in that direction. And graphically, without ever knowing what the formula or the equation for this function is, graphically, I want to explore what's going to happen with stuff like the limit as x approaches 0 of f of x, and I want to talk about the limit as x approaches 3 of f of x, and I want to talk about the limit as x approaches -2 of f of x. So we'll just go down the list. Limit as x approaches 0 means what does the function look like it's doing when x is 0? When x is 0, it looks like the function should be 0. It looks like it's just going to be my intercept there. So I'm pretty confident saying that that should be 0. There's no squirrely business, there's no funny nonsense going on. It's 0, so the limit's 0 and we're all set. The limit when x approaches 3 of f of x is going to be a little more interesting. Because if we talk about what the function looks like it's doing, it looks like it's going up really, really tall. How high does it get? There's no bound on how high it gets. It goes up forever. It gets infinitely tall. Are we allowed to say that it reaches infinity? We probably shouldn't, because infinity is not a number, and functions output numbers. You put numbers into them, you get numbers out of them. Functions are about numbers. So if this thing goes up to infinity, we probably shouldn't say that it gets to infinity and that infinity is the output of this function. So f of 3 equals infinity. This is frowned upon. This doesn't make a ton of sense. We shouldn't say it. It's not mathematically correct. But we're doing limits. And limits are fake math that were invented for us to break these rules. So, can we say that the limit of f of x as x approaches 3 is infinity? We can and we should. So there you go. That's what limit does for us. In the continuing theme of this is a concept that lets us break the rules, we're breaking more rules. We still can't say that f of 3 is infinity, but we can say the limit is infinity when x approaches 3. That's fair. This one's going to be even more exciting for us. One of the things we talked about yesterday in the last video is whether when the neutral limit, I should say, for the neutral limit to exist, you need both of the directional limits. Where's my other hand? Yeah, there. Gotta get both hands in frame. You need both of the directional limits to exist and to agree. If they both exist but they're going to different places, then you don't get a neutral limit. So you need them to exist and agree in order to get a neutral limit, which is kind of why we have the limit as x approaches 3 is infinity here. Because from the left, it's going up to infinity, and from the right, it's going up to infinity. So, like, these things don't exist in the sense that they're not numbers, but they do agree on this idea of a concept, so we're going to call that good. For the -2 case, we're going to have a bit of a problem, because from the left, it looks like we're going up to to infinity, and from the right, it looks like we're going down to positive or negative infinity. I just screwed up all of that. That entire sentence was wrong. From the left, it goes up to positive infinity. From the right, it goes down to negative infinity. So these things exist, lots of quotation marks on that one, in the sense that they are infinity, but they don't agree. One of them is positive infinity, one of them is negative infinity. So we still say that this does not exist. But we can talk about the directional limits here. The limit as x approaches -2 from the right is negative infinity. And the limit as x approaches -2 from the left is positive infinity. So we can do the directional limits back here at -2. We'll get negative infinity, we'll get positive infinity. Because they don't agree, we say that the neutral limit does not exist. In this case, the directional limits do agree, so we can say that this limit is infinity. And if you're going to do a point that's not one of these weird places, like x equals 3 has weird nonsense going on, x equals -2 has weird nonsense going on, because those are our two asymptotes. If you want to pick literally any number that isn't 3 or -2, then your limit is just the function value. There's no weirdness you have to account for, you're all set. You can just find the value on the graph. Like if we wanted to do the limit of as x approaches 1, that would just be 1. So this is a special case for vertical asymptote, weird shenanigan stuff. So there's a couple more things we need to talk about. First thing we should talk about is the other kind of function that has vertical asymptotes. this is y equals the natural log of x minus 3, quantity plus 4. We remember from our days of doing transformations that this is 3 right and 4 up. So if I wanted to do a graph of this, 1, 2, 3, 3 to the right is going to put my vertical asymptote at x equals 3. 4 up is going to put what used to be my intercept here at the point 4, 4. And aside from that, it's going to have a very standard issue logarithm shape. So the question about this is the limit of f of x, or I should say the limit of y, I guess. I've named this thing y. The limit of y as x approaches 3. This is what I want you to think about for a second. As long as we're doing infinite limits. And now, having thought about it for a second, I'm wondering if you said that the limit was negative infinity. If you did say that this limit is negative infinity, you would sadly be incorrect. It is not. This limit does not exist. Because negative 3 only has, the function only exists on one side of negative 3. In order for this neutral limit to exist, we would need both of these things plunging down towards negative infinity. So we can talk about the limit of y as x approaches 3 from the right. This is very safely negative infinity. But this neutral limit does not exist because log functions typically only exist on one side of their asymptote. So if you want to talk about this limit, you have to use directional limits. Last thing we need to talk about briefly in section 2.4 is how to do this analytically. What we've just done on the board is about graphical limits. If you're looking at a graph, how can you determine what the limits are for whether they are infinity or negative infinity, or if you're doing the mixed direction thing, then the limit does not exist, that sort of thing. We need to talk about what you do if you don't have a graph. All you have is a function. So if we have something like f of x equals x plus 4 minus x minus 5, I think at this point I could pretty safely ask you for the limit of f of x as x approaches 1, and you would very dutifully plan A this and tell me that this is 5 over negative 4, which is that. So no problems here. But then if I asked you for the limit of f of x as x approaches 5, you can already see that plan A is going to fail. When we plug the 5 into this denominator, it's not going to work. You can probably also already see that this cannot be simplified. There's no factoring we can do. There's no weird nonsense we could try to pull with conjugates. There's really nothing we can do to that. So plan B is going to be exactly as successful as plan A. So that's also going to fail. So we could go straight to plan C to determine that this limit does not exist. But because we're in section 2.4 and we need to account for the possibility that these things are infinite in one direction or another, we should check to see what's going on. And we're going to do that by plugging in numbers that are just a little bit to the right of 5 and a little bit to the left of 5. So if we plug in a number like 5.1. So let me do this. It does not exist. But consider a number like 5.1. If we plug in a number like 5.1, we're going to have f of 5.1 should be, let me pause and back up for just a second here. The reason we're plugging in numbers is, if we're in this plan C situation with a rational function, we know that we got there because there's a vertical asymptote at this value, x equals 5. The only way limits don't exist on rational functions is because there's vertical asymptotes there. Otherwise we would just have a point or a hole, which would be a plan A or a plan B solution. So if we're in plan C, we know we have a vertical asymptote. We know it's going to be either doing both up to positive infinity or both down to negative infinity, or one of each like this or one of each like this. Those are the only way we can do these vertical asymptotes. 4 options. So 2 of these 4 options have limits. If it's both going up, the limit is infinity. If they're both going down, it's negative infinity. If they're doing a crisscross maneuver, then there's no limit, does not exist at all. So because we have this vertical asymptote and we're trying to explore more about it, we can plug in a number on either side of 5, really close to 5. And the nice thing about plugging in this number is I don't actually care what the result is. I have no interest in the actual number for f of 5.1. The only thing I'm interested in is whether or not the result is positive or negative. If it's positive 100 or if it's positive 2, it doesn't make a difference. Positive numbers mean it's going up, and that's all I care about. If it's negative 1,000 or negative 10 million, it still doesn't make a difference. All I care about is whether it's positive or negative. That'll tell me what kind of behavior I have near this asymptote, and that will let me determine whether or not the limit exists. So we'll try 5.1. When I plug in 5.1, I will get something that's close to 9 and something that is just barely positive. So I know that's positive. And when I try 4.9-ish, f of 4.9 should give me something that's almost 9 and something that's just barely negative. So that will give me a negative answer. So at 5, to the right of 5 I'm going up, to the left of 5 I'm going down. So I know that this limit definitely does not exist. But I now know that the limit of f of x as x approaches 5 from the right is infinity, and the limit of f of x as x approaches 5 from the left is negative infinity. And the neutral limit does not exist because they do not agree. This is pretty much all you have to do for evaluating these analytically. You get to your plan C situation and then you plug in some numbers nearby to see what kind of asymptotic behavior you have. Make your decision based on that. That's going to do it for this video. Stay tuned for section 2.5 where we talk about even more exciting nonsense with infinity.